All right, so this is part 9 of Unit 2, and after this video, there's only one more video in Unit 2. In this video, we're going to be looking at properties of logarithms, and then we will also be solving exponential and logarithmic equations. Now, the first thing we're going to look at is expanding and condensing logarithms. And so we're going to be using these rules here. The first rule here we have is if we have a logarithm with any base here, and we have two things on the inside that are being multiplied, then what we can do is we can expand those using addition. So if it's log base b of m times n in the inside here, then we can rewrite this as log base b of m plus log base b of n. So whatever was first and then whatever was second. If we have division, then that expands to subtraction, and whatever is in the denominator gets expanded with subtraction, whatever's in the numerator with addition. And then the last property we're going to use here is that exponents can be changed into multiplication. So any exponent up here can be moved down in front of the logarithm. And that exponent has to be on the whole thing here. So if you had something like log base 5 of x squared plus 2, something like that, this exponent could not come out front. If you had an exponent out here, that's what could come out front. Now, one other common misconception with these is that if you have something added inside, you can separate it with addition. That's not the case. Those are not equal. What you can only do is if something's multiplied on the inside, then it expands to addition. So multiplication expands to addition, and division expands to subtraction. And the reason I made these arrows going both ways is because not only can we expand logarithms, but we can condense. We can go the other direction. So if we have two things being added together and they have the same base, then we can condense it using multiplication. And we will go both directions. We'll use both of those properties. One more thing that we don't use a whole lot anymore, and that's because graphing calculators now typically allow you to change the base, but they used to not do that. You used to have to use what's called the change of base property in order to use a calculator. So the change of base property allows you to change the base to whatever you want or change it to natural logarithms. So first we're going to look at some examples where we are expanding logarithms. And again, we're going to be using those properties of multiplication going to addition and division going to subtraction and powers coming out front. So the very first thing we're going to do here is I have x times y cubed, log base b. I can go ahead and expand that to log base b of x plus log base b of y cubed. And if I stopped right there, I would not get full credit because there's one more step we can do. We can bring this exponent out front. So log base b of x plus 3 log base b of y. And that is fully expanded. The next example here, we have natural logarithms, and these rules work with natural logarithms as well. So I have x cubed and y on top. Those will be expanded using addition, and then anything on the bottom with subtraction. So natural log of x cubed plus the natural log of y minus the natural log of z squared. And those exponents can move out front. So 3 natural log of x plus natural log of y minus 2 natural log of z. And then the next one, we've got a more complicated expression here, but it's not too bad. First, we have natural log of 100 times x cubed times the cube root of 5 minus x. And then on bottom, we have x plus 3 to the 5th power. So everything on top will be using addition, everything on bottom using subtraction. So the natural log of 100 plus the natural log of x cubed. And sometimes I'll see people keep those together. They'll write 100x cubed, but those could be separated as well. So we want to expand it as much as possible. And then plus natural log of, I could write the cube root of 5 minus x, but I'm going to change that instead of the cube root. That's the same thing as to the 1/3 power. And we're going to do it that way so that we can move that exponent out front. And then minus the natural log of x plus 3 to the 5th power. So the only thing I have left to do is bring those exponents out front. And then we have it as expanded as it can be. All right, now we're going to go the other direction. Now we will have it already expanded, and we will want to condense it. So we go in the opposite order. The first thing I'm going to do is bring exponents back. So log of x plus log of y to the 7th power. And then this is addition, so I can condense that with multiplication. Okay. And remember, if you don't see a base there, that's assuming it's base 10. Now remember, if I had written this as log of x, y, and then the 7 out here, that's not the same thing, because in this case, I would have the 7 being applied to both the y, or x and the y, but it shouldn't be. There's no 7 power on the x. So make sure that you don't write it like this. It should just be like that. All right, the next one, we have these exponents here that need to go up top. So the 8 goes back up here, and the 4 goes back on the x. So I will have the natural log of x plus 9 to the 8th power minus the natural log of x to the 4th power. And anything that is expanded with subtraction will then go to the denominator. So this will become the natural log of x plus 9 to the 8th power over x to the 4th power. Now, another mistake that I sometimes see students make when they are condensing here is instead of writing this where it's one logarithm and parentheses around the whole fraction, what they will write is the natural log of x plus 9 to the 8th power over the natural log of x to the 4th power. And that's not the same thing. Those are not equal. These are not two separate logarithms. It's one logarithm condensed together. Okay. All right, one more. Here we have a 1/3 being applied to everything, and I'm actually going to do that step last, but these exponents out front on the inside, actually there's just one, we'll go ahead and move up. So I'll have 1/3, and I'll have the natural log of x plus 6 to the 5th power minus the natural log of x minus the natural log of x squared minus 25. And then everything with a negative on it is going to be in the bottom. So we'll have 1/3 natural log, and we'll have x plus 6 to the 5th power up top, and then x times x squared minus 25 on bottom. And then the last step is this 1/3. Now remember, if I bring that 1/3 on a power to this whole thing here, then something to the 1/3 power is the same thing as the cube root. All right, so that is expanding and condensing logarithms. And we're going to be using those properties in logarithmic equations in this next part here. And those will become smaller parts to larger problems. So, all right, so this next section here is going to be looking at exponential and logarithmic equations and their applications. And we're going to be using these 4 tools here. Now, this first one is for exponential equations, and then this last one is for exponential equations, and then these middle 2 are for log equations. So if we have an exponential equation, that's something like this here, where we have something to a power and something, and it could also have a power here, or it could just be a number. There's no logarithms in this equation. So these are actually, this whole first page are all examples of exponential equations. This page here is examples of logarithmic equations. There's logs in all of those equations. So the first and the last tool are for exponential equations, and then the middle 2 are for log equations. Now the first tool is, if we can rewrite this so that the bases are the same, then if each side just has one term with one base and then exponents, and the bases are the same, then that means the exponents also have to be equal. And then that'll be an easier equation for us to solve. If it's not possible to do this, so this would be like first choice or option 1, then if it's not possible to do that, then what we can do is take the log or the natural log of both sides of our equation, and that'll be our other tool here. So for our first example here, we have 5 to the power of 3x minus 6, and that's equal to 125. So what we're going to do here is try and rewrite these bases so that they are the same. Now, we know 5 can't be rewritten as any smaller base. 5 can't be broken down any smaller than 5. But 125 can be rewritten as 5 to the third power. That's the same thing as 125. So 5 to the power of 3x minus 6 is equal to 5 to the power of 3. Now my bases are the same, and once my bases are the same, then that means my exponents have to be equal to each other. So if the bases are the same, then I can go ahead and set 3x minus 6 equal to 3. I can add 6 to both sides, and then I have 3x equals 9. Dividing by 3, x equals 3. Now, one more thing I meant to mention about logarithmic equations. We have to check our answer. And that's because we can't plug anything into a logarithm. We can't have the inside of a logarithm be negative. So we have to be careful about plugging in our answers. So we have to check our answers there. But for exponential equations, we don't have that problem. Exponential equations have the domain of negative infinity to positive infinity. So we don't have to go through the process of checking those answers. For the next question here, it's not possible to rewrite 8 as 4 to some power. 4 to the first power is 4. 4 squared is 16, so that's already bigger than 8. But it is possible that we could rewrite both of these numbers. 4 is 2 squared, and 8 is 2 cubed, and now they have the same base. Well, we have 8. Again, 2 cubed is the same thing as 8 to the power of x plus 2. And then 4 is the same thing as 2 squared to the power of x minus 3. And then remember our exponent rules. If you have a power to another power, that gets multiplied. So 3x, and then 3 times 2 is 6, is equal to 2x, and then 2 times 3 is 6. So I can subtract 2x, I can subtract 6, those cancel, and I have 3x minus 2x is x, and on this side equals negative 12. Okay. Now the next one is our first example where we get something, or where we have numbers that we can't rewrite as the same base. 5 can't be broken down any smaller, and 134 is not equal to 5 to any power. We can't write that as 5 to the, third power, fourth power, fifth power, something like that. So what we're going to have to do here is use our other option. We're going to take the log or natural log. It's up to you. I'm going to use the natural log of both sides. And now I can use that power rule. So I have the natural log of 5 to the power of x, and I can bring that exponent out front. So I have x natural log of 5 equals the natural log of 134. And remember, our goal here is to solve for x. That's what means, what we mean by solving an equation. So when I have x equals 12, I solved for x. So I want to get x by itself. Now, if I had this equation, log or natural log of 5, that just represents a number. If you type that in your calculator, you're going to get a decimal. If you type in natural log of 134, you're going to get a decimal. So what we really have is something like, let me do this in pencil so I can erase it. If I had, let's say, 6 times x equals 18. Well, if we had something like that, then we could divide both sides by 6, and then we'd have x by itself, and that would be 3. That's essentially what we have here. This is a number, this is a number, so x times a number equals a number. We're just going to divide by that on both sides. So let me go ahead and erase all that pencil here. And I'm going to go ahead and divide by natural log of 5. And I have x is equal to the natural log of 134 over the natural log of 5. Now you cannot write this as one logarithm. This is not equal to ln of 134 over 5. That's not the same thing. So don't write that. That's not equal to what we have here. You have to have two separate logarithms. In this case, this is not where we're condensing. Okay, so this is your exact answer. And then we're going to type that into our calculator, natural log of 134, close parentheses, divided by natural log of 5. And when we do that, we will get approximately 3.04. Now, on your quizzes and tests, I want to see both of these. I want to see the exact answer before anything has been rounded or anything like that. And then your approximate answer. That's what this squiggly equal sign means, is that it's approximated. It's about 3.04. We had to round that decimal, so it's no longer an exact answer. So I want to see both of those on a quiz or an exam. For the next example here, 10 to the power of x and 8,000. Well, there's no way for us to rewrite 8,000 as 10 to some power. If it was 1,000 or 10,000, then yes, we could, but it's not. It's 10 to the power of x and 8,000. So what we are going to have to do then is take the log or natural log of both sides, and I'm going to take the log, and I'll explain why I'm choosing log instead of natural log in just a second. So I have log of 10 to the power of x. That x can come out front, equals log of 8,000. Now remember, if we have a logarithm where we're not writing the base, we're assuming it's base 10. And if those two numbers are the same, base 10 of 10, then that's equal to 1. Well, if that's equal to 1, 1 times x is just x, and that's equal to log of 8,000. So that's my exact answer. Let me go ahead and type that in my calculator to get my approximate answer. And that should be 3.903. Okay. We usually round somewhere between 2 and 4 decimal places. All right, so this next example looks a little bit different. It's a little bit, or has a little bit more steps to it. In this case, we don't have just one term on this side. Every other equation we've looked at, it's been one term and one term. Well, now in this case, we have two terms on this side, but what I can go ahead and do is add 3 to both sides. And 237 plus 3 is 240. And then I have this coefficient of 40 on the base of my exponent. I want just something to a power. I don't want a number out front. So I'm going to go ahead and divide by 40 on both sides. And 240 divided by 4 is 6. And in this case, I'm going to go ahead and take the natural log of both sides. And the reason I'm choosing natural log is because I have an e here. So I can go ahead and bring my 6x out front. And natural log of e, well, those bases and that are the same, so that's equal to 1. So natural log of e is just 1, so 6x times 1 is just 6x. And that's equal to natural log of 6. I can go ahead and divide by 6 on both sides, and x is equal to the natural log of 6 over 6. Now, I cannot cross these 6's out. That's not something we can do here because this 6 is inside this logarithm. It's inside of that function, whereas this 6 is not. So that's kind of like if we had the square root of 6 over 6, we couldn't cross out those 6's either because this is inside of square root, this one's not. Same kind of thing here. This 6 is inside the natural logarithm, this 6 is not, so we couldn't cancel those out either. All right, so that's my exact answer. I can type that into my calculator, and you should get about 2.99. Okay. All right, let's do some more examples. We've got a couple more where we have an exponential equation here. This next one we have 5 to the power of x minus 2 equals 4 to the power of 2x plus 3. And here, again, we have an example where we cannot write these numbers as the same base. 5 and 4 can't be written as the same base. So I'm going to go ahead and take the natural log of both sides. And in this case, you could either use log or natural log. It doesn't matter. And I'm going to bring my exponents out front. And what we need to be careful of here is we have two terms in the exponent. It's not just x or 2x or something like that. It's x minus 2. So we have x minus 2 times the natural log of 5 equals 2x plus 3 times the natural log of 4. And in this case, if I had something like x plus 3 times 4, I would distribute the 4 onto both of those terms. And so what I need to do then, since natural log of 5 and natural log of 4 both just represent numbers, this needs to be distributed onto both of those terms. So I have x natural log of 5 minus 2 natural log of 5 equals to x natural log of 4 plus 3 natural log of 4. Now, if I had an equation where I had x's and numbers on both sides, let's say I have something like 2x plus 5 equals 7x minus 3. What I would do is I would try to get all my x's on one side, and I'd try to get all my numbers on the other side, and I'd have 5x over here, and I'd have 8 over here, and I'd divide by 5. So that's essentially what we have here. I have a term with an x, I have just a number. I have a term with an x, I have just a number. So I'm going to try and get all the terms with x's on one side and all the terms with just numbers on the other side. So we have this term with an x and this term with an x. I'm going to go ahead and subtract 2x ln 4 minus 2x ln 4 from both sides. And I'm going to add 2 ln 5 plus 2 ln 5 to both sides. And then what we have on this side is x ln 5 minus 2x ln 4 equals 3 ln 4 plus 2 ln 5. Now both terms over here have an x, and I'm trying to solve for x. So they have a common factor of x. I'm going to factor that out, and what I'm left with is ln 5 minus 2 ln 4. And now I just have one x that I can solve for. Well, this just represents a number, and this just represents a number, and that's x, so I can divide by this number onto the other side. So I have x is equal to 3 ln 4 plus 2 ln 5 over ln 5 minus 2 ln 4. And when I type this in my calculator, you want to make sure to put parentheses around this whole thing, and then your division symbol, and then parentheses around this whole thing. Because your computer or your calculator does not know order of operations, and so you want to make sure that you use order of operations here. Okay. Now it is possible you can condense this. You can move your exponents up, and addition condenses to multiplication, division condenses to subtraction condenses to division, but you don't need to. So I'm fine if you leave it just like this. You don't need to do that extra work. This is the exact answer I would want to see. And then you type that into your calculator, and when you do, you should get 9.21. So again, I'd want to see both of those. And it's really to your benefit that I see both of those, because if you didn't show me your exact answer, but you made a calculation error and you got a wrong number here, if I don't see that exact answer, I can't give you full credit. So if I see your exact answer is correct, but you made an error in your calculation, I'll still give you full credit. On the other hand, if your answer here, maybe you condensed it, or maybe you did write this in a different way, or maybe your solving looks a little bit different, and your exact answer looks different from my answer key, but I can see that your number here is correct, then it gives me reason to go and check that this is correct, and check through all of the steps of your work and make sure that that's correct. So it's really for your benefit to show both of these to ensure that you get as many points as possible. All right, the next one, This one looks very different from the rest of them, and we're going to use a different technique with this problem. So we have e to the power of 2x, e to the power of x, and then just a constant. This equation here is actually a quadratic pattern. Now, we've been doing quadratic patterns since our first week of class of this semester. This e to the 2x, e to the x, and then the 7, if we let's say u, this is called a u substitution. When you take calculus, you'll use u substitutions a lot. If we let u be equal to e to the power of x, then e to the power of x we can rewrite as 8u plus 7 equals 0. And then e to the power of x squared would be e to the power of 2x. So that would be u squared. Now that's a quadratic equation that we can use the x method for. If you use the x method on this, 7, negative 8, that's negative 1 and negative 8. Or I'm sorry, negative 7, not negative 8. And so factoring that, that would be u minus 1 and u minus 7. Well, then we get u equals 1 and u equals 7. Now we're not trying to solve those equations, we're trying to solve it with e to the power of x. So remember, u is equal to e to the x. So e to the x equals 1 and e to the x equals 7. Those are the two equations we're solving. Now if we take the natural log of both sides, these are two separate equations here. Well, natural log of e to the power of x, that's just x, and the natural log of 1 is 0. So this one gives us x equals 0. If I take the natural log here, that cancels and I just have x is equal to natural log of 7. And I could type that in my calculator and get an exact answer. In this case, I would just leave it like that, but you could get a decimal answer as well. All right, next one, we have log equations now. And so if you go back to that, the previous page here where we had all those rules, now we're not using the first and the last rule anymore. We're going to be using these two middle rules. So there's two different approaches here. If we have the logarithm on both sides, so I have one logarithm on this side and one logarithm on this side, and they have the same base, then this rule is kind of like that first one, where if it's log same base, log same base, then that means the inside also has to be equal. But if we have a logarithm on one side and then just a number or something else on the other side that does not have a logarithm on it, then we're going to use the snail rule to rewrite it as an exponential equation. So we'll use the snail rule and rewrite it that way. So this first one, we have a log on one side and a number on the other. So this is going to be where we use the snail rule. So 2 to the power of 3 equals x minus 4. And if you need a refresher on the snail rule, we went over that in the last video, I believe. Well, 2 to the power of 3 is 8. And I can add 4. And x is equal to 12. And so in this case, we need to make sure we check our answer, because like we said, anytime we have a log equation, we have to check our answer. And what we're checking for is to make sure that when we plug it in, we don't have a negative number in here. Well, 12 minus 4 is 8. 8 is not negative, so this is fine. Now, when we have a logarithm on one side and a number on the other, we don't want to have a coefficient out front like we do here. So if you do have something out front, we want to divide that over. So I just have a logarithm and a number. So I'm going to divide both sides by 4. And the 4's cancel. I have the natural log of 3x is equal to 2. And now I can use the snail rule. Remember, the base for a natural log is e. So e to the power of 2 equals 3x. I can divide by 3. And x is equal to e squared over 3. And if I plug that in my calculator to get a decimal, I should get 2.46. Okay. All right, the next one, we have two logarithms on this side and a number on this side. And if we have something like that, what we need to do then is condense this to one logarithm. We can't use the snail rule if we have two separate logarithms, because then it's like, well, which one do we use? How do we do that? So we need to condense this first, and addition condenses to multiplication. So I have log of x times x minus 3 is x squared minus 3x equals 1. And remember, if you don't see a number here, we're assuming base 10. So 10 to the power of 1 equals x squared minus 3x. And then from there, I have a quadratic equation. So what I need to do is get this set equal to 0. So if I subtract 10 over, I have 0 equals x squared minus 3x minus 10. If I use the x method to factor that, I get x minus 5 and x plus 2. So x equals 5 and x equals negative 2. So I need to check my answers. Now, just because I get a negative answer doesn't mean that's necessarily a problem. It is possible to get a negative answer here, but when you plug it in, it doesn't make what's inside negative. But in this case, if I do plug in negative 2, log of negative 2, we can't do that. We can't take the log of a negative number. Negative 2 here, negative 2 minus 3 is negative 5. All it takes is one of them to make it not work. So it's not that it has to not work for both of them. It just means there needs to be one that it doesn't work for. If I plug in 5, log of 5 is fine. And 5 minus 3 is 2. That's positive still. So this is a solution. This one is not. One more, last example here. And here we have logarithm, logarithm, logarithm. There's logarithms on every term. And if that is the case, then what we want to do is have one logarithm on this side, one logarithm on this side, and set the insides equal. Subtraction condenses to division, so I can rewrite this as the natural log of x plus 2 over 4x plus 3. And then here, natural log of 1 over x. And if it's natural log equals natural log, then that means this is equal to this. So x plus 2 over 4x plus 3 is equal to 1 over x. And then we can go ahead and cross multiply. So x plus 2 times x is going to be x squared plus 2x. And then 1 times 4x plus 3 is just 4x plus 3. This is a quadratic equation, so we want to set it equal to 0. So I subtract 4x. Subtract 3, and I get x squared minus 2x plus 3. Oops, minus 3, not plus 3. Equals 0. We have to factor x minus 3 and x plus 1. And so from there, we get x equals negative 1 and x equals 3. Again, we need to check our answers. If I plug in negative 1, 1 divided by negative 1 is a negative, so that's a problem. That one does not work. If I plug in 3, 1/3, well, that's positive still. That's fine. If I plug in 3, 4 times 3 is 12, plus 3 is 15. That's positive. That's fine. And then 3 plus 2, that's 5. That's positive. That's fine. So this one is a solution. It is possible that both answers would work. It's possible that neither answer would work, and then you would have no solutions. So it's not always the case that one will not work and one will work. It could be that both work. It could be that neither work. All right, and that brings us to the end of part 9.